Today's lab is the common emitter amplifier design lab using the 2N3904 BJT. If you've done the pre-lab calculations and simulations, you already know all the components you need here. One thing to note is that the analog discovery module can't do 15 volt supply. The best it can do is plus 5 volts and minus 5 volts DC, which I hadn't really considered until now. But I think all of our components will still work reasonably well as long as you manage to pick them up from the lab. So just to go over here what this looked like, these were the calculations I came up with for the components. And to note, for the hardware, I didn't have a 27K resistor, but I put 3 10K resistors in series in order to get kind of close. So that's 30K instead. And RC, I didn't have 820 ohms, so I tried 1K first, and that seemed to be too high, so I ended up putting 2 1Ks in parallel and ended up with around 500 ohms here instead. And with those small modifications, I think I've gotten things to run. It's not going to perform the same as what you originally designed it to be, just because we don't have the correct supply voltage, but it will work reasonably well. So this VCC will become 5 volts, and instead of ground here, this will be minus 5 volts. And this load resistor I connect to ground instead of the minus 5. But that's just for easier measurement of the output signal, so it doesn't have a DC offset to it. But with that, let me show you my hardware here. Okay, so I'll give you a brief overview first. I've constructed things similarly to the way the schematic looks, but I know it's messy, so it's a bit hard to follow. The BJT is in the center here, with the base going over to the left, the collectors up top, and the emitters on the bottom. This is RE1, this is RE2, oops, that's the capacitor, this is RE2, and here's the shorting capacitor across RE2. The base is in here, and let me move this white wire out of the way. So the base connects to R2, which is right here. This is a 10K resistor, and that goes to the negative supply, which is the white wire from the analog discovery module. And I have an orange wire going across to connect all the emitter resistors down there. On the positive side, R1 is made up of 3 series 10K resistors, like I mentioned before, and that connects up to the red wire, which is the positive 5 volt supply. Additionally, we have our coupling capacitor here, which couples the base to our input signal, which is the waveform generator from the analog discovery, which is yellow. And I also have the scope monitor, the orange one, which is channel 1 on this signal. Over here we have the collector stuff up top, and I mentioned I put 2 1K resistors in parallel here, and those connect up to the positive supply through this orange wire. There's also the load resistor over here coupled through this capacitor, and so this resistor right here is the load, that's the 10K, and that connects up here to my ground input. So I have the black wire from the analog discovery, that's ground, and then I also have the orange and the blue wires from channel 1 and channel 2 of the scope, because those are also, you want those referenced to ground as well. And then also here, this blue one, this is channel 2 of the scope, that's connecting to the top of the resistor, so we can monitor that signal. So I know it's a lot and it looks messy, but can use this as a reference to help you guys through it. And I'll kind of zoom around a little bit here, if this will focus, so you can get a better view of what's going on. These 3 resistors here, if you got your components from the lab right, you can replace with just one. I made do with what I had for this video. As I said, this orange wire connects the 2 sides together, and that connects up to there where the RE resistors meet. To note, these are on separate rows. Notice the emitter is not on the same row as where the coupling cap goes to. It's 1 row below it. I just put it in that location just for my ease. Okay. And there's all the stuff up top and the ground. Okay, a lot to digest, but if you put this together yourself, you'll probably come up with something similar, hopefully. You can just use this as a reference. Okay, so I already have the analog discovery stuff up. Let's refocus here, and let me pull that up here. So here I've set the plus and minus 5 volt supplies, and I've got 100 millivolt amplitude, 10 kilohertz sine wave going in, 0 volt offset, and I'm measuring on the scope channel 1 and channel 2. Channel 1 is the input, which is 200 millivolts peak to peak, and channel 2 is the output, which is about 2 volts peak to peak. So I still managed to get a gain close to 20. It's a little more than 20 actually, maybe. Yeah, it's a little more than 20. So you can export this data if you'd like. Workspace, settings. I forget where the export was. Oh, extract. Nope, that's not it. Save as. Nope, that's not it. Somewhere I exported the data before. Oh, well, it's right here on the side too, I guess. Oh, I was looking in the wrong spot. Okay. So you can export here under the scope options in order to look at the data. And you can get why did everything turn off? I don't understand. Okay. Anyway, you can use that data to figure out the gain of the circuit. Alright, so the other part of the lab is to increase the input signal until you get clipping to occur, basically, because you want to see what the maximum output swing is. And because the supply voltage is limited with the analog discovery module, you're not going to meet your swing requirements. So don't worry about it, just figure out where it clips, basically. And we'll see where it clips in both directions. So we'll increase this a bit further, maybe 300 millivolts. You might have to adjust the scale here. Oh, it looks like it can go a little further, maybe. It can go quite a ways in the negative direction. I think we hit it. Oh, no, not yet. There we go. Now we're clipping here. So the peak to peak swing is about 8 volts here, but we clipped on the positive side really early on. So if you want to just see where that clips, it was under 200 millivolts input. Because there's 200. So if we try 150, it's starting to level off there. And at that point, the peak to peak output swing is around 4 volts, so not nearly as good as what you would hope for, basically. And I think you could do some fine tuning about the RC value. I'll try taking out one of my RC resistors here and see if it makes things any better or worse. So this is with 1K now instead of 2 1Ks in parallel. And it looks to be a little bit better, so might be able to go a little bit further now. And it kind of clips symmetrically, which is kind of nice. Anyway, so we go back to our lab data collection, and we need some pictures here. So here you can just put the approximate value for the resistors. If you have no way of measuring them, that's okay. You can leave that blank. Picture of your hardware, just get a picture of your breadboard circuit. And you need an image with 200 millivolts peak to peak input, which is what I started with. And a picture with a larger input so that you can show the clipping at the output. And just measure your gain before you start clipping when you have the 200 millivolts peak to peak input signal. And that's it for this lab.